Okay, so let's talk about the lab. So if you want to plan ahead, the test over all of this will be next Thursday. Okay, so we've got another big 2-day lab, which will consume tomorrow on Friday. Don't get excited. It sounds like it's a drug deal, but it's not. But it does involve something called crystal violet. But don't flip out. It's cool. Okay, no, not the 60s. But it is kind of cool because it's a slow reaction that fades, and you can figure out the order that reaction is there. But that takes a couple of days to do that lab as well. And then we've got some odds and ends stuff to figure out. We review, boom, test on Thursday. So there's that. So the lab from last 2 days. So here's like the big picture of various aspects of the lab that you figured out. So first thing you hopefully figured out is that the general form of the reaction is K, and it's based upon the concentration of the acetone and the concentration of the hydronium ion. So this is a classic situation where if you just looked at the overall reaction, which said that the acetone plus the iodine, if you look at that on that front page, you get this new structure of acetone, basically where you have a carbon, and instead of 3 hydrogens, you swap that out for an iodine, and then you generate an additional hydronium ion and another iodine. So basically what happened in the short version, here, let's kind of build the structure. Kind of give you a visual. So here was one end of the acetone molecule. It's got groups of 3 hydrogens around it. And then you have an iodine, which is the molecular form of this. So basically what happens is that 2 things have to happen. You have to break the bonds that hold the iodine together, because if you don't break these bonds, the reaction can't happen. So that takes a certain input of energy, which is what was said next. So I'm just going to begin to plant this seed right now. In the chemistry world, unlike the biology world, you have to put energy in when you break bonds, but you release energy when you form bonds. Okay? So it takes a certain amount of energy to break the bonds that hold the iodine together. So these come apart. These are now separated. So what's going to happen is that this is going to come in, and it's going to kick out one of the hydrogen atoms, and that's going to take its place. So now you have this iodide ion floating around, which doesn't have a color to it. So the molecular form of the iodine is that brownish color. The iodine is still in there, but it's not the elemental form, and that's when it goes clear, when all that iodine changes into iodide. So you're not changing the number of iodine molecules in terms of particles, you're just changing the rearrangement of them. And that's the cool thing about this. And there's two cool things about this particular reaction. One, it's slow enough that we can get a good measurement of the reaction. It also involves a color of iodine that we can readily observe. This would be impossible to do with this technique if everything was clear. Like if we tried to do this with like sodium hydroxide and hydrochloric acid, you'd make salt water. Great. That would be tough to measure that rate because you wouldn't see any noticeable changes. So this is why we used iodine. So what's going to happen is that you're going to basically make hydroiodic acid. You're going to make a hydronium ion, and you're going to make an iodide ion. Well, why do we write those as separate ions?
They exist ionized.
Why? Because it's a strong acid. Because iodine basically has no desire whatsoever to take the hydrogen ion back in. If we had made, like for example, hydrofluoric acid, which would be tough to do with fluorine because of the fact that number one, it's highly poisonous, and I really don't want to subject you guys to hydrochloric gas. But if we did this and we had made hydrofluoric, then over here we would have written that as the molecular form of HF. Okay, if it had been hydrofluoric, but it's not hydroiodic, that's why I write them in separate points. So, here's the deal. If this is all you saw, and this is in terms of vocabulary, if this is all you saw, and you don't, and this is it, this is all you've got, you would think that the rate should be first order with respect to the acetone, because there's a 1 in front of that, and you would expect it to be first order with respect to iodide, because there's 1 in there. So if this was a one-step reaction, the rate would be acetone times the concentration of the iodine, boom, there you go. But hopefully what you saw is that, oh man, we can change the concentration of the iodine, but it doesn't change the rate. But I don't want you to have this idea, it's like, oh, well, who cares about the iodine? Whatever, doesn't affect the rate. It's not as important. No, the iodine still has to be there. The iodine has to be present for the reaction to take place. It just doesn't alter the rate. So don't confuse something being in the reaction versus something that alters the rate. That's why it's 0 order with respect to iodine. So this is where the chemistry, more complex side of the chemistry kicks in. Like, well, we figured out that it was actually dependent upon the hydronium ion concentration, which you wouldn't think of based upon the initial reaction. So what that tells us is at some point, there's another reaction where the hydronium ion has to get consumed, okay? Something has to consume that hydronium ion, which is why you added hydrochloric acid. Because just based upon this reaction, if I said, hey, I want you to go do this reaction, you would only ask for 2 things. You would only ask for acetone and you would ask for iodine. Based upon that reaction, you would not ask for hydrochloric acid. You're like, nope, don't need it. Acetone, iodine, hydrochloric acid will make that later. Okay? But in reality, and this is one of the things that you have to figure out in terms of steps, like we actually do need that, but this is why we added hydrochloric acid. The chlorine is just going to be a spectator ion in this whole thing. Okay? Don't care about the chlorine. What we do care about is the hydronium ion. So we have to add the hydronium ions because back behind the curtain with the wizard pulling the handles, there has to be a wizard behind the curtain with a handle that says, hey, I need hydronium ions. That's why you added the hydrochloric acid. It doesn't show up in the overall reaction, but we needed it in some sub-steps behind the curtain to make the reaction take place. Okay, so with this lab, here's one of the most important things I got to stress to you. Show your work, write down the units, okay, because everybody's datas, everybody's times are all over the place, okay? I don't have an answer key. I know what your answers generally should be, but the only thing I can really grade you on is the process, okay? That's the most important thing. So you did that, figured out the order. Then you said, okay, cool, great. Now let's use that to make a prediction, which all went well, except whose group went way?
Big Mike.
Big Mike.
No, that's not us, right?
Yeah, you predicted what, 300 some odd seconds, and it took like 30?
Yeah.
Oh, okay.
Forget to like.
I have, congratulations, in all the years of doing this lab, I've never seen one that off, okay? Usually it's in within like 3 or 4 seconds of the predicted time. So I have no idea what happened with that one. Okay. Now, next is the activation energy, which is the basis of what we're going to talk about today. So you can think of activation energy, and we're going to draw this graph a lot today. So this is energy, and this is like the progress of the reaction. So the reactants have a certain amount of energy, and I'm just going to put this as just generic reactants, whatever they are. Okay? Could be water, could be hydrogen and oxygen, could be acetone, whatever. So you can think of this as being like a roller coaster. So the activation energy, which we call E sub A, is how much energy you have to put into the reaction to get it started. Okay? So that's like the height of the roller coaster. How high does this thing go up? It's a big, and that's what we visualized the other day. I said, okay, right? So if I don't hit this hard enough, I don't get a reaction because it's like I don't get the roller coaster up the hill. But if I overcome that activation energy, then I start the reaction. So the activation energy is the height of the hill. Now, just like any roller coaster that goes up, roller coaster must come down. So when you get done, either you can end up here with a higher energy state, or you can end up way down here in a lower energy state. We'll talk more about that tomorrow. But for now, or today, all I need you to know for now is the activation energy is the height of the hill. But that's tough to determine, like, based upon our observation. It isn't like we can look at this reaction and go, oh, right, I can see that, okay? It isn't like we can visually see the roller coaster. So we have to find a mathematical way to do that. So what you should have done on graph paper, you had 3 different trials, and you had 3 different K values. So on here, you should have the natural log of the 3 K values, and then 1 over temperature in Kelvin, okay? So these numbers here are going to be pretty small numbers. And some of the data that I've looked at is actually surprisingly linear. You're going to plot those points. You're going to draw a line of best fit. The slope of the line is going to come from the line of best fit, not from your data, okay? The only time you could use your data to determine the slope is if your data actually happen to fit on the line of best fit. If it doesn't, you can't use your data, but the point being is that you should see, I should be able to look and see, hey, which points did you pick to find that slope? So, when I did my calculations off my data, I had a slope of around 2.5 times 10 to the 4th Kelvin, right? That's what I had as my slope. And there's a huge variance in the slope, okay? But that at least kind of gives you a ballpark. So if you have a slope of 5, something is horribly wrong, okay? Something has gone horribly wrong.
What about 1?
Well, that's even worse. You have a slope of 1.
Like 1 times 10 to the 4th.
Oh, I can live with that. I thought you said you had a slope of 1. And I'm going, oh, well, Stanley, that's bad. Okay, I can live with that. It's just as long as it's not something times 10 to the 4th. I literally thought you had a slope of 1, and I'm going, really? Okay, but that is not the activation energy. That's just the slope of the line. So the whole thing, and this is Isaac.
Sorry, does the slope of the line represent K, but not really?
It is in Kelvin, but it's not the temperature.
Okay.
But it has units of Kelvin. It's a little weird, but it makes the units work out.
Okay.
Because the actual full-blown equation is the natural log of K equals negative E sub A over R times 1 over temperature in Kelvin plus the natural log of A. Okay? Don't worry about the natural log of A part. That's your y-intercept. We'll talk about that later. Okay? Don't worry about that for now. Not part of the story. Your part of the story is this right here. So this is just a fancy, very, 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 very fancy way of saying y equals mx plus b. Okay? It's just a linear function. Okay? But we don't, and this is why we graphed natural log of K on the y-axis and why we put 1 over temperature in Kelvin on the x-axis, because that's what we have to graph. So when you get the slope, which should be a negative value, okay? So when you get that slope equals negative E sub A over R. R is your gas law constant, but it needs to be the physics R, not the chemistry R. Okay? So the physics R is 8.314 joules per mole Kelvin. This is why this has to be in Kelvin in terms of that slope, because then you multiply joules per mole Kelvin by Kelvin, the Kelvin cancels out, and then you get joules per mole. Okay? So it's kind of a unit sleight of hand, but it works. So your activation energy, what I got, was around 2 times 10 to the 5th. Okay? So as long as you are somewhere close to that, I'm good with it. But again, more importantly, let me see the process. That's what I can grade, is the process. Okay? On the questions like the 4 factors that affect the rate of the chemical reaction, if you're not sure what they are, read the lab. Okay? Take Mike. Anyway, your answer to number 10 on that last page should be a really big number, okay? A really, really big number. And here was the point of this question. So assuming the reaction is first order with respect to acetone and using the theoretical value K of that, what is the half-life of the reaction? Okay, that's going to be a really big number. And again, this is just the half-life. This is not how long it would take for the reaction to go to completion. This is how long it would take for half of the acetone to be consumed. Just half of it. Not all of it, just half. And that's a really, 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 really big number. So if that was the actual answer, that was the actual situation, we would start this reaction on Monday, and maybe by the following Monday, the iodine might be consumed. Okay? It would take a long time. You talk about one boring experiment. Okay? It's like watching rust form, right? What are you doing watching rust? Exciting. Cool. Right? So this is the whole point then of question number 11. Okay? Is this a reasonable assumption? Okay? That's what I want you to think of. Is like, not so much. Okay? All right. Any questions? Staple the lab to the back. Get that handed in. Mark, you stop the camera.